Welcome to Lecture B8. This is where we will begin to really consider some of the main ideas of probability. In this lecture, specifically, we will be talking about experiments, outcomes, and events. If you look in your book, they define an experiment as a process of measurement or observation. Now, when you make this measurement or observation, there are different values that you can measure, and those are outcomes. And then different sets of outcomes, different collections of outcomes, are what are referred to as events. Or to be a little bit more specific, the sample space is the set of all possible outcomes for an experiment, and the events are subsets of the sample space. So let's try to clarify some of these ideas. First of all, let's write a few of them down, and then we'll look at some problems. So again, S is equal to the sample space, and it is equal to the set of all possible outcomes for an experiment. And an event is a subset of S. An outcome is a simple event. So to clarify some of these ideas, let's look at problem 24.2.2. And the experiment here is tossing two coins. So first, let's identify S. Remember that S is equal to the set of all possible outcomes, and so we can denote it like this. If we toss two coins, one possible outcome is heads and heads. Another one is heads on the first coin and tails on the second coin. Another one is tails and heads, which means tails for the first coin and heads for the second coin. And then the final possible outcome is tails and tails. So here's the sample space. It is the set of all possible outcomes. Now, the events, subsets of S, are called events. So, one example of an event is the collection consisting of heads, tails, and tails, heads, because that is a subset of S. Now, one example of an outcome is simply heads, tails. That's one outcome. So you can see that what we call an outcome is a simple event. It's an event that has only one element in it. Now let's look at some other examples here. Let's look at problem 24.2.8. And here we will, in fact, actually, even in problem 24.2.2, the one we've already done, all that we were really asked to do in that problem was to identify the sample space, but we went ahead and gave an example of an event and an example of an outcome as well. But in problem 24.2.8, we will simply identify the sample space. So the experiment in this problem is choosing a committee of 2 from a group of 5 people. Now, let's call those 5 people A, B, C, D, and E. Now, I strongly encourage you to stop the video now and try to find the sample space yourself, and then come back to the video and let's look at it all together. Okay, so I hope you had luck with that. And the answer would be this. If we have 5 people, and we call those 5 people A, B, C, D, and E, then the sample space so the sample space in that case would be the following. We could have A, B. That's one committee of 2. Or A, C. Or A, D. Or A, E. We could also have B, C, B, D, B, E. We could have C, D, C, E, and finally we could have D, E. And that's the sample space for problem 24.2.8. Now, I want to go ahead. This is a perfect opportunity to show you something else we'll return to later in this chapter. Let's look at the number of elements in the sample space. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in S. 10 elements, 10 different ways we can choose a committee of 2 out of a group of 5 people. Well, we could have figured this out in advance using the following formula. When you're choosing, let's say, number of ways to choose a group of M people, we'll say committee, a committee of M people out of a group of n people, that is given the symbol that symbol. Now that symbol that is when people look at that symbol, what they say is n choose m, and it is equal to n factorial over m factorial times n minus m factorial. Here it's understood that m is less than or equal to n. And so in the problem that we just did, we would have 5 choose 2, which would be 5 factorial over 2 factorial times 5 minus 2 factorial, which is 5 factorial over 2 factorial times 3 factorial, or 5 times 4 times 3 factorial over 2 factorial times 3 factorial. Of course, the 3 factorials will cancel, and so we get 5 times 4 over 2 factorial, or 20 over 2 times 1, which is 20 over 2, which is indeed 10, which of course is the number of elements in S. So this is a handy thing to know, and is something we will return to several times in this chapter. A final problem I'd like to consider in chapter 24.2 is 24.2.10. It introduces a new idea. It says, in rolling 3 dice, are the events A sum divisible by 3, and B sum divisible by 5, mutually exclusive. Now, I really want you, let me actually tell you this. In doing problems in probability, I believe that the real key is practice, practice, practice. Is really something. There are many different ways to think about probability problems, and the way to get accustomed to approaching problems when there are so many different ways to approach to think about them is by practicing, by getting lots of experience with it. And so I very definitely strongly encourage you to stop the video here, think about how you would approach this problem and try to answer it, and then we'll all look at it together. Okay, so I hope that you had some luck looking at this problem, and I'll show you the way that I would approach it. There could be ways that others would approach it, different ways, but I'll show you the way that I would approach it. Now, first of all, for rolling 3 dice, I would want to, since I want to look at these two events, A, which is that the sum is divisible by 3, and B, the sum is divisible by 5, I would want, probably just to be on the safe side, I'd start by considering the sample space and then identifying A and B. So let's look at the sample space. Remember now, we're going to roll 3 dice. Now, I guess actually right away we can see that trying to list the entire sample space is impractical. Why? Well, you have 6 different values that the first die could assume, 1, 2, 3, 4, 5, and 6. 6 different values that the second die could assume, 1, 2, 3, 4, 5, and 6. And then the same 6 values for the third die. And therefore, the number of elements in the sample space would be 6 times 6 times 6, or 6 times 36. And I guess that would be 216 elements. And we certainly don't want to list all 216 elements of the sample space. So let's not begin, after all, let's not begin by listing S. Let's go ahead and list A and B. Okay, A. What will be the outcomes that will be included in the event A, which is that the sum is divisible by 3? Well, one outcome would be 1, 1, 1, meaning that the first die has a value of 1, the second die has a value of 1, and the third die has a value of 1. If that is the case, then obviously the sum is divisible by 3. That's the only way that the sum will be divisible by 3. And so now, the next situation we need to consider that would be included in A is if the sum is equal to 6. I might have just misstated something, so let me begin again. This 1, 1, 1 is the only event where the sum would be equal to 3 itself. We have a number of events where the sum is divisible by 3, but 1, 1, 1 is the only event in which the sum is equal exactly to 3. Okay, so now we want to look at the events where the sum is equal to 6. And so let's say, okay, 1, 1, 4 is one possibility. Another one would be 1, 4, 1. And another one would be 4, 1, 1. Then we would also have 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. 3, 2, 1. Now, can you think of, again, this first event gives us a sum of 3. All of these events, 1, 1, 4, 1, 4, 1, 4, 1, 1, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, those are the events that give us, those events give us a total of 6. Can you think of any others where we have 3 die and we get a total of 6? I believe the answer is no. So now we'll look for a total of 9. And actually, I believe, to be honest, even this is beginning to get a little bit tedious. So let's just go ahead and try to have even more insight into this problem. You know, if the total is 3, then any outcome where the total is 3, like 1, 1, 1, which in fact is the only outcome with a total of 3, that will be in A, but it's not in B because the sum is not divisible by 5. And likewise, all of these events that we've noted here, they are in A because the sum is equal to 6, but those events would not be in B either because 6 is not divisible by 5. And in fact, if we listed the events that were had a total of equal to 9, that wouldn't work either. In fact, the first case we have to consider is where the total is equal to 15. And let's think about that. Is there a way that we could get 15? And of course, the answer is yes. If we had 15, So we'll say, note that the outcome 5, 5, 5. Now, this is not the only way we could get 15. We could also have 4, 5, 6, 4, 6, 5, 6, 5, 4, 6, 4, 5, and what we could have 6. Well, we could have 6 in any one of the three, for any one of the three variable 3 die. And so there's several other possibilities, but we don't need to list all of those because the question here is mutually exclusive. And the only way that A and B are mutually exclusive would be if there's not a single event that they have in common. But here we have found an event, not a single outcome that they have in common. But this outcome, the outcome 555, and I'll say, and several others, such as 4, 5, 6, 4, 6, 5, 5, 4, 6, 5, 6, 4, etc., and others are in both A and B. Therefore, A and B are not mutually exclusive. The only way that A and B would be mutually exclusive would be if the event A and the event B had no outcomes in common. But there are several outcomes that are in common to the event A and the event B, and therefore these are not mutually exclusive. Now, let me ask you a follow-up question, though. If we were rolling 2 dice instead of 3, if we were rolling 2 dice, would these events be mutually exclusive? And in that case, the answer is yes. Because with 2 dice, notice that, as we've already noticed, as we've already seen, the first sum that is in common to both A and B would be 15, but you can't get a sum of 15 with 2 dice. And therefore, if you had only 2 dice, the events A and B would be mutually exclusive, but with 3 dice, they are not. So make sure you understand that. So now let's look at some problems for this section. Problem 8-B8-1 is how many outcomes are in the sample space for the experiment consisting of tossing 3 coins. The choice A is 6, choice B is 3, choice C is 5, and choice D is 8. And for problem 8-2, how many outcomes are in the sample space for the experiment consisting of rolling 2 dice? Choice A is 36, choice B is 12, choice C is 64, and choice D is 6 to the 6th power. And problem 8-B8-3 will be given in class. So that concludes lecture B-8, and good luck.